Hello, everyone. Welcome to the Competing on Bitcoin podcast. I am here today with my good friend and partner, Sergio Lerner.
Hi, Johnny. How are you doing?
I'm doing awesome. What about yourself?
Excellent. Fantastic. Couldn't be better.
Tudo bem. Awesome.
Tudo
So,
legal.
I believe that for those who are familiar with the Bitcoin and blockchain world, Sergio does not need an introduction, so I will make it very short. Sergio is one of the authors of the original BitVMX paper and of many subsequent improvements of BitVMX. He's here with us today to discuss ESSPI, which is one of such improvements. BitVMX FORCE is a coalition to drive BitVMX evolution and to foster its adoption. Sergio is one of the Jedis behind the BitVMX FORCE. So before we start, let me say and clarify for you all that this conversation will be quite technical. I will try to stay at a high level most of the times, but I will not prevent Sergio from digging as deep as he wants into any specific question that I may ask him. Without further ado, let's start this beautiful session. I will assume some familiarity with disputable computing and one-time signature schemes. And if you read the ESSPI paper, which was published in March this year, things will be much easier for everybody. So, although we assume some familiarity with BitVMX, and the disputable computing paradigm in general, let's start by quickly reviewing BitVMX. Sergio, what is BitVMX and how does it work? Just do it in 2 minutes and 37 or 38 seconds if possible.
Okay, so hi everyone. So BitVMX is a way to verify arbitrary computations on top of Bitcoin. So we managed to use the existent Bitcoin smart contracts without any soft work or without any addition to verify computation, and that happens off chain, and to be able to challenge that computation on chain in case of misbehavior. So we can have two parties or any number of parties, and one wants to assess certain fact, like I withdraw a certain amount of funds from a sidechain, etc. Anything we want to prove, and then the prover just puts this this data in the Bitcoin blockchain, and then the other participants, if they agree, they do nothing. So the protocol is called optimistic because in that case, it's very, very efficient. But if there is dispute, if some of the challengers detects that there is a misbehavior from the one posting the proof, then they enter a dispute, what we call a dispute channel between them, where basically one of them wins. And if the challenger wins, the prover can be penalized, can be slashed or whatever mechanism you want. And if the prover succeeds in his proof, basically the challenger can be slashed and the contract finally executes, which is what the prover wants. So I think that the importance of this scheme and the difference between this scheme and other schemes is that this is very, very efficient. The amount of actual data that is posted on Bitcoin blockchain and the computation that happens on the Bitcoin blockchain is rather small. It's in the order of tens or hundreds of kilobytes. So, and in terms of dollars, it's like about $500 in the case of a dispute. So it's just the most efficient protocol to verify computation in Bitcoin that exists today.
Wow, awesome. Good, thanks. The idea here is to try to dive deep into ESSPI, and we are almost there. But I think it's always useful to start the conversation by having a glimpse of the impact of the innovation we are going to be talking about. So before moving into the nitty-gritty of ESSPI. Can you give us a preview of real-world use cases that would benefit the most from ESSPI, just so we have a good way to start the conversation and start digging deeper into what ESSPI is and how does it work?
Yeah, so I can avoid being a little bit technical about this, but the thing is that when you design a system for verifying arbitrary computations on top of Bitcoin, you want the system to be as flexible as possible. You want not only to support certain specific cryptographic scheme like a SNARK, you want it to support Starks or Foley schemes or Nova or Hypernova, anything that comes later. And why this is so important? Because over the last 5 years, I would say the cryptographic schemes to prove computation have been improved so much. Like every year we have almost a tenfold improvement in efficiency. So being stuck with a certain system, a certain proving system, which also has specific security assumptions which are not great, like trusted setup, etc., it's not something we want. We want general purpose verification systems, and that's what BitVMX already provides. So here is the thing: to be able to verify any other of these schemes, like a Stark, you need to post on Bitcoin a higher amount of data. A SNARK, you can create a SNARK with just 128 bytes, and that's enough to to prove a fact with a SNARK. But when you want to use some other systems like Stark, you may need to post 80 kilobytes of proof to be able to natively verify that. And the thing is that to post information, you have to sign it with Internet signatures. That's the only mechanism that exists until ESSPI to be able to get this information signed and into a smart contracts in Bitcoin. And this is terribly inefficient. Well, it means that the expansion factor for every single byte of proof that I want to put and I want to verify, I need 200 bytes.
What about Lamport?
Well, Lamport is just as inefficient as Winternet. It's just a little bit more inefficient. Like Winternet signature is just packing several, I could say, several Lamport bits together into a single chain instead of just a single bit. So it's kind of a little bit, it's about a 50% improvement. But we are talking about, a 200, even 200 bytes per single byte that I want to sign. So that is prohibitive for anything but SNARKs. So all the other systems, you would see that they just verify SNARKs. They cannot verify anything else. And if they want to verify anything else, they just pass it through a SNARK verifier in the last step. While we actually, with ESSPI, we changed that.
Let me interrupt you for a second.
Yeah.
So the reason for that is because the inputs in all the other schemes are signed with Winternet or Lamport.
Well, there's two things. You have schemes that are specifically built to verify SNARKs and nothing else. Like the whole script just is a SNARK verifier. So you are stuck with that. And then you may have some other schemes that they do have input, like they can receive a SNARK, like BitVM1, but still they do this expansion, enormous expansion on the size of the input. So with ESSPI, what we have is that we can have a general purpose protocol such as BitVMX, but now we can get the input with no expansion at all. Like we have a constant signature, which is small, very small compared to the data of the proof, like 65 bytes compared to 100 kilobytes of data. And this data is just thrown into a Bitcoin transactions and just you sign the transaction. That's the whole trick. Is just reuse Bitcoin transaction signing, which are either signed by ACDSA or by Schnorr, and just use it from the smart contract. And this is completely new.
That's interesting. Can you summarize then the main technical innovations in ESSPI?
Yeah.
The things that you feel or are different and enable ESSPI to do things that all these other schemes or all these other protocols cannot do?
Yeah, so it's interesting because to solve the problem, we had to like overcome many difficulties. Like Bitcoin has a lot of restrictions, a lot of things you cannot do, or they are non-standard. We always want to stick to standard transactions. So, for instance, it's one of the problems is how to, I mean, if you have information that is signed by Schnorr, how can you make sure that the same information can be brought into BitVM or BitVMX smart contracts? And so you have to take the hash of this information and sign it again with Winternitz. But instead of signing the whole information, you just sign a hash. And the trick here is how you can prove that the Schnorr signature of the hash is equivalent as the Winternitz signature of a hash without actually bringing the whole message again. Like if we have a 1 megabyte message and I want to prove that these two signatures are equivalent, I don't want to give you the whole megabyte because I would need to sign it with Winternitz to put to get it into a smart contract. I don't know if I'm clear with this. So the trick here, one of the key tricks is how do I compare two signatures? How do I make sure these two signatures are actually signing the same data without giving you the data? And that's amazing. But the second thing that we have to solve is, okay, now we have a virtual machine, the BitVMX virtual machine that runs RISC-V instructions. And now I have an input that it's that we only have a signature of the hash, but we do have a signature. How do I prove that, to this machine that the actual data that I'm reading from memory, from a buffer that is supposed to come from the external world, is actually signed by this hash? So we had to put a hashing core into the CPU, right? So we have a new instruction into the CPU that actually performs one of the compressor functions of SHA-2056. So we have a small piece of circuit, I would say, embedded into our code that performs this operation. And then we can use those instructions, these new instructions, into the code. And what happens is that we are able to verify that the input is correctly signed, only having a signature of the hash inside the CPU. If you read the paper, maybe it's clearer there, right? Because I don't have a board to draw things, but essentially that's the idea. And we inside this process, there is a new fraud proofs where you have to prove that the hashing was made correctly, and so there is a binary search, a partition search within this new protocol to pinpoint if there is a misbehavior in how the hash instruction is working. Then you basically can pinpoint the place and enter a dispute and resolve the dispute. So these are the two main advances here. But I must tell you, they are very tricky. And there's a lot of nitty little details that make the system work that we had to go very deep into the Bitcoin, how the Bitcoin protocol actually works.
How did you arrive at this novel approach? What inspired you first to explore ECDSA and Schnorr instead of Lamport and Winternitz, or as alternatives to Lamport and Winternitz? How did it all start?
Yeah, so
driver?
So maybe you hear about this. There's two worlds on Bitcoin script. What is called the small script and the big script. And these two worlds that exist inside Bitcoin script there's almost no communication with that. So it's like having two data types in a programming language that you cannot move through one to the other or connect or compare or anything. And this is because Satoshi removed these opcodes that reach the gap between these two data types, the big data and the small data. Small data is just 4 bytes. It's 32 bits, and big data can be anything up to 500 bytes. And so every person that works with Bitcoin script, every researcher is always trying to come up with ideas on how to bridge these two worlds. And so the challenge here was always present, is how do I bring information from a bigger world, like a big chunk of data in a transaction, into the smaller world of small script Bitcoin, right? And that's a challenge. But this is a group effort. Futo participated. He was the one who had the idea on how to challenge the hashing core inside the CPU. Also, Martin collaborated with the new transaction DAG and how that should be connected. And so it's a teamwork here. So I don't know who invented each part, but there are several moving parts that are very interesting here.
For just out of curiosity, for how long were you working on this? How long do you think it took you from the seminal ideas until publishing the paper?
Well, the first idea, I think it was I don't know how the idea started, but I think Futo had the kickstarting idea on how to do it. But then we discussed a lot for almost a month without coming up with a really simple solution, because solution would get complicated up to a point where we would say, okay, let's drop it and start over, right? But once we had a simple solution for the hashing core and how to challenge the hashing inside the CPU, then the other was just, I would say, hard work and working with details, which is basically the part that I collaborated most was just solving every single detail because it relates how the Bitcoin protocol works. So that took like a month of just going through every single detail, and we could have worked more. There is continuations to this work that we couldn't put on the first paper. So several ideas were left for future improvements, right?
I'll ask you about that in a second. Just a comment about having the privilege of watching you guys come up with this. It's so much fun, and I don't know, just as you describe, the idea is born. You start ping-ponging this, and then Futo comes up with this crazy thing out of nowhere that you know how the hell
you saw us with the whiteboard, right? Drawing stuff all the time. Yeah.
No, but yeah, I've been seeing it for maybe my entire life working with you guys. So and then you just grab it and do your magic, and Martin does his thing, and I think that yeah, it's for me it's as I said, it's a privilege, and it's a lot of fun to see the amount of creativity.
I think that in all these works that are pretty complex, when you talk to someone, when you work with someone, you just generally find your flaws on your own reasoning. So it's much easier when you work with someone, because at the time you try to explain something, it's the time it breaks, right? So I think it's collaboration here was key.
Yeah, and that's where I was going, to the synergy of this team, and how things happen just by working together and collaborating. That's what I think it's so valuable in this team. So let's talk a little bit about the fact that the paper mentions that BitVMX operates in a two-party setting, right?
Yeah.
Can it be extended to more than two parties?
Yeah. So that's a property of BitVMX, that essentially the easiest and the more decentralized way is two-party, because each one can penalize the other party and there is no third party involved. It's like you can prove anything that it is fully decentralized when there is two parties. When there is more parties, then it gets a little tricky, because you can have a collusion between parties. So the protocol works in a setting where there is one honest party is enough to protect the protocol, like to protect the funds. So if everyone except you are malicious, then you are fine, as long as you respond on time and you challenge other malicious activity. And that works for BitVMX, and for BitVMX plus ESSPI, it's the same. What we have in BitVMX when there are multiple parties is what we call the dispute channels. So if there is a number of parties, there is the square number of dispute channels between them. Like if there's 10 parties, then there is 10 by 10, 100, 10 by 9, I would say, 90 dispute channels that could be used in practice to dispute the other party. And what is interesting is that it doesn't matter if we participate in one protocol instance or 1,000 protocol instance. If the same group of parties is participating in all protocol instances, then we still need the square number of n square dispute channels, because once you dispute with a party and you win or you lose, you will never dispute the party again, because one of the two parties is going to be slashed and it's going to be taken out of the protocol. So this is very efficient, and it gets more efficient when you participate in more and more instances of BitVMX. So that makes breaches very efficient. Like you can have 100 begins, 1,000 begins, 10,000 begins, and the number of dispute channels stays constant, stays fixed. So that's one of the features of BitVMX.
Cool.
But
Cool.
that applies to BitVMX and BitVMX plus ESSPI, to both of them.
Yeah. Good. So let's go back to a more pure ESSPI part of the conversation. Can you share with us a little bit more about ESSPI's security? Specifically, is there any cryptographic assumption or primitives that you have relied on to ensure ESSPI security? How confident are you in its robustness? Share with us a little bit your thoughts on ESSPI and security.
Yeah, it essentially does not add any other cryptographic assumption. I mean, there is a couple of tricks that you may want to, but you don't need really. For instance, one of the interesting things is that Bitcoin double hashes some data, like applies the hashing twice, and we tap into the middle of that, for instance. So that could be something, but essentially other parts of the Bitcoin protocol only use one hash function, not two, the newer ones. So doesn't change the real security assumptions there. And there are some tricks that you could do to prove certain facts, that you could use 3-start collisions assumption instead of normal hash function assumption. You could do that, but essentially it doesn't change. You can do it without that. So no, I wouldn't say there are more assumptions. There is only one strong assumption in BitVMX and BitVM2 and any of these optimistic protocols, is that there won't be minor censorship for long intervals, like for days or weeks. You won't be censored. Your transactions won't be censored. And in that regard, I can say that BitVMX is much better than the others because we use standard Bitcoin transactions. So we don't need to knock the doors of miners and tell them, oh, could you include my non-standard transaction that other protocols need. So that's good for BitVMX. We just use standard, and not only standard, they are pretty small. So it would be very, very hard or just to think about anything blocking those transactions. Okay, so no, the short answer is that there's no more security assumptions with the ESSPI. Even sorry to interrupt. It might be much better instead of in security assumption, because if you are going to verify a star directly, then you don't need a trusted setup. You don't need to go through a snark. So that makes the system much more the security much more aligned with Bitcoin's ethos, right? No trusted setup. A proof that works, or essentially you could verify bullet proofs, which are based on the same discrete log problem that elliptic curves signatures. So basically, you could use this with the same security assumptions as Bitcoin and verify any external computation. So Bitcoins will love this.
Can you walk us through how does ESSPI enable the verification of start or of any other uncompressed input?
Okay, so how it works in the virtual CPU is that you essentially have a memory mapped area of the virtual memory of this virtual CPU, which is a RISC-V CPU, that it gets mapped with the input that the prover is, or the prover or the verifier, because we allow prover and verifier to provide inputs to the program. So that gets memory mapped. So in the BitVMX program, when you are using ESSPI, you have two sections. The first section, the only goal is to hash this memory buffer, this memory mapped input buffer, to hash it, and then check against the Winternitz sign hash. And that, I would say that part of the code would be like standard, a preamble to any BitVMX program. And you will just use the same code over and over because it's just a library function. And then when you make sure that you have a assurance that the input buffer contains assigned data that was signed, then the following part of the program can access freely to those memory locations that are previously already verified to have the correct value and use that. So in the second part, basically you would just take a snark verifier, a Stark verifier written in Rust or whatever language that can compile to RISC-V, and just run the verifier. It's as easy. It's so easy. Like if you take a look at a Docker image of how this works, and you would see that it's super simple. You only have to run it locally once to make sure that you have the trace. But even if you are going to execute like 100 billion instructions, first, you don't need to store the full trace. You could store just checkpoints in the trace. So basically, you can recompute at any time from a certain point. And the number of the rounds that you are going to execute on chain is logarithmic with the number of trace steps you create. So essentially, it doesn't matter if you execute 1 billion instructions, 100 billion instructions. It's going to be like between 5 and 10 rounds on chain. And why I say 5 and 10 rounds, and we are moving to another topic, is because we have several improvements in the pipeline to do to BitVMX, hopefully before the end of the year, to reduce the number of rounds.
So, as a way to kind of summarize some of the things we were discussing and to put it in comparative ways, focusing on efficiency and scalability, BitVMX plus ESSPI, how does it compare to the other schemes that are out there?
Okay, so let's say you would like to verify a Stark on Bitcoin directly without going through a snark. So currently that's impossible. So we make it possible. Even if you had OpCat, and this is a work that Starkware did, even if you had OpCat, the number of opcodes, Bitcoin opcodes you need, script opcodes you need to verify a Stark is 3.5 million. Okay, so that makes that it's a block full of opcodes, right? Only to verify a single Stark. And actually, if we use ESSPI, then it would take less. It's a state-of-the-art version of this, like the one we will have probably by the end of the year. That would take like 200 kilobytes. So it's the efficiency and the cost, it would be incredibly lower. I don't know how what are current Bitcoin fees, but I think you spend like in the case of the other solution, like $20K on transaction fees just to verify. It's like even if you had a CAT, and in our case would be just $200 or something.
So what you're saying is that it is possible to verify a start on Bitcoin without a soft fork?
Without a soft fork, we do it without a soft fork, of course.
Yeah.
And
I just wanted to emphasize that.
And I published an article like a week ago about how Opcat improves our BitVMX protocol, and it does a lot. So it wouldn't be 200 bytes; it was much less probably, because I'm not considering that if we are comparing apples to apples, like having Opcat in both, then BitVMX it's really like a few kilobytes, right? Combined with checksync from stack, that would be like 4 kilobytes for BitVMX groups. But I don't expect that to happen like in the next 1 or 2 years. It's Bitcoin hard forks are very rare, and if they ever happen, sorry, Bitcoin soft forks in this case. But if they occur, and I would love to occur, but we have to be very realistic here. Like Bitcoin is ossifying, and any change to Bitcoin may take years or may never happen. So the good thing about BitVMX is it just works right now, and its efficiency as it is right now.
That's awesome. Do you foresee ESSPI plus BitVMX or its components being standardized or adopted widely within the Bitcoin ecosystem or other blockchain platforms?
Yeah, I think all the technologies we are using are open source, free of IP, no tokens, nothing strange to a Bitcoiner. Like it is Rust, RISC-V. It's all kind of open technologies. So and we are putting this in the SDK, very easy to use. So I would say that why not? Why wouldn't this be part of the development stack for any Bitcoiner? It's just one additional tool that you may use, right? It's like having a new language or a new feature. You just take it and use it, and it's fully open source, decentralized. But that doesn't mean that we need as many collaborators as we can. Like if you want to participate, then come and help us. If you are a company and want to collaborate with BitVMX FORCE, then of course that would be great, because it all takes time and effort, and publishing papers takes time, takes research time. It all
So
it's not easy.
You as a BitVMX FORCE Jedi are inviting all other developers, researchers who would like to contribute and collaborate with us to join us at the BitVMX FORCE. Can you tell us a little bit more about what the plans are for BitVMX FORCE, or what is it about? What's the intention? Why does it exist? You as the Yoda.
So there is the technical reasons, and I would say the community reasons. Like from the technical perspective, we have 2 papers we want to publish this year with key innovations that will reduce to a 1/4 of the number of rounds the protocol requires, which is great. So that needs obviously resources and programmers and testers and everything, and obviously it's good if people collaborate with that. But also I think that for any of these protocols to be widely used and standardized, you need to do some community effort, like create hackathons and invite people to look at your code, maybe put bug bounties so that people can get rewarded from reviewing your code. So that all obviously needs resources also. So I would say that it's necessary in this stance. Yeah.
Cool. Awesome. So I will emphasize that the BitVMX FORCE welcomes you all if you want to contribute to this effort where we believe.
Should we use like lightsabers, like
I
Star
think we
Wars?
should.
That could be our icon, right?
You see, we gotta work on that. We gotta work on that. We need that. But we are not aggressive. It's not that we're going to use those against anybody. It's just, for us to show that we are part of of the
I don't know.
line.
Bitcoiners can get aggressive sometimes. I might take it with me.
But it's at least to to prevent others from attacking, as a dissuasive element. So, what are the planned enhancements and extensions you mentioned in this conversation that before the end of the year there are 2-3 papers coming up with innovations, but let's be not extremely specific, but because we don't have the time and probably you cannot do it here, but let's share with us a little bit more about what are those planned enhancements and extensions to ESSPI and
I would say, yeah. So we have two kinds of improvements here. What I call incremental improvements and what I call radical improvements. So I would leave aside the radical ideas we have, like that basically it changed everything and it makes it so much better, and we are working on that, but I'm not going to talk about that. Maybe in a couple of months we will, when we publish something, but I'm more about now the incremental things, right? So there are 3 incremental papers that imply incremental changes, incremental improvements. I will cite 2 of them. The first one is called interleaved disputes or interleaved verification games, where basically instead of having one party proposing, the mid states or the intervals, and the other party choosing which one of them is the one that he finds a dispute, he pinpoints a malicious step and repeating that. Instead of doing that, we let both parties collaborate and propose intervals, and that makes the protocol use half of the rounds. So that's one, and that not only applies to BitVMX, it applies to any verification game. And what is funny here is that no one is using these ideas, so that would be a good thing. And the other thing is that in BitVMX we decided to use memory coherence, memory verification system, which was very easy to implement in Bitcoin script, which is basically it's based on a hash chain, and it's a very simple data structure, and which makes it very easy to verify on Bitcoin. But when we have to verify a memory access, then we have to perform a second NRE search, a second partition search, and which basically doubles the number of rounds. So I come up with a new data structure, an authenticated data structure that allows you to travel in logarithmic links or logarithmic time between 2 pair of nodes of the trace, adding just 1 link per node. But this is a new data. It's very rare when you design a new data structure, right? Never happened to me in my life to really create something that not only applies to your field, but it applies to any algorithm or data structure book, right? So this new data structure allows you to do that. You have a chain, and then you have 1 additional link per node of the chain that connects back to 1 point. And basically the question is, how do you how can you move from 1 point to another in a logarithmic number of steps? And we solve that with a new data structure. And when we apply this data structure, what I call the jump list, into the BitVMX protocol, we get half the number of rounds, because we don't need to perform this secondary search. So these 2 things together combined reduce the number of rounds to 1/4 of the original protocol. And the idea is to have this ready by the end of the year.
That's cool. All right, so before we start getting into the wrap-up section of this episode, is there anything that you would like to tell us about, to share with us?
Well, I would say 1 year ago, I remember I said, expect innovation that changes everything. Expect the unexpected, right? And I would repeat it, right? There were still early times. these protocols will grow. There is a lot to do and lots of ideas that need to be researched and proven. So you can expect having completely new versions of BitBMX by next year with things that are maybe you think today that are not possible, and we make it possible. But not obviously not only our team, but other teams will also propose new fantastic ideas. And the good thing is about collaboration, and we do a lot from BitVMX FORCE, collaborate with the other projects doing research on BitVM, is that each time someone proposes something new, the others can take it and use it and get the protocols all get better. Right. So for instance, the ESSPI idea is already being used by one of the bridge projects to improve their bridge that is using BitVM2, for instance. So everything we do and everything other teams do, we collaborate and we improve our protocols, because the end game, the end result here is to make Bitcoin a really an open financial system, and not only store of value, but just payments and DeFi, everything that people needs, and brings really financial inclusion on top of Bitcoin, and do not force people to go into centralized exchanges and centralized custodians, which is against the original ethos of Bitcoin. So we are all together in this. And even if we are working sometimes in competing projects, we are not actually competing. We are everyone is trying to improve Bitcoin and make it more accessible and easy for the average people to work with and to keep their funds secure, right?
Yeah, and to have a better world, right?
Yeah, totally.
Good. Okay, so finally, any word for developers or researchers that are inspired by the work that BitVMX FORCE is doing? What advice would you give them?
Mm-hmm.
If they want to build an ESSPI or explore similar optimizations in blockchain protocols?
Yeah, I would say we are very close to publishing a fully usable SDK where you can just bring your idea and deploy it on BitVMX and test it. So we are so close that I would say just use it, right? When it's ready, test it. If you have the idea to use this for a new type of payment channel, more private payment channels, or payment channels that are more efficient, or new types of bridges, or new type of liquidity pools where you pull together your funds to do something. Any idea you have, you probably can make good use of BitVMX to verify your business logic on the Bitcoin blockchain without even moving your assets into another chain. So yeah, I follow us, follow our work, and use it. And then if you are to have your time and expertise to come to contribute, yeah, we will be more than happy to have your pull request reviewed.
Good, awesome, Sergio. I think we had a very interesting conversation. I feel we touch on different parts of the same general topic. I believe there is a room, or there is an opportunity for new conversations and to focus on specific things that we touch during the past 45 minutes. Let's keep it for a follow-up, for a new episode. Thank you very much. It's a pleasure to have you in this conversation with me, and it's a pleasure to be working together on this.
Thank you, Jony, for inviting me. And please, if you have any doubt, maybe you can post the Telegram channel after this is published, so that anyone that has a question, the best way is obviously through the Telegram channel, because if it's not me, it's some other of the developers that can give you the answer. So yeah, that would be great if you have questions to come to the Telegram channel.
Thank you.
Thank to you. Bye-bye.
Bye.